Spoken. I think I cannot hear you, Ken, if you're trying to share out there.
Hello.
Hey, Ken. So let's meet at 3 o'clock and then go from there. That's reasonable. Can you hear me, Ken?
Sorry. Yes. That's perfect. Yeah, that works for me. Thank you for agreeing to meet with me today.
And then I think what I'm going to do is I'm thinking of changing off with my office hours so that it is more accessible, or else let's talk about it at 3 o'clock and then go from there.
Okay.
Okay. So we have homework 3. February 9th. That's Tuesday. And midterm. Midterm is still away. About 3 weeks after the homework is due. And we introduced the a broad idea of functional derivative last time. Today I want to do lots of examples so that I can clarify that whatever we mean and how we want to use it also. So notice that like it's like talking about derivative. When we learn derivative for the first time, we use ab initio principles, but then we have a standard prescription. And after that, just using that is most often sufficient. That's not mean that it is always true. So whenever there is a confusion, sometimes there could be a discontinuous function, and then you want to go back and look at the basics and see what exactly does this mean. But 99% of the time, it is sufficient to use some prescription and get through. So similarly, we have introduced the idea of a functional derivative very broadly speaking, and we want to have a handle on the use of that. As we noticed last time, there was the idea of delta function that showed up. So let me very quickly go through delta function. Again, delta function itself is a very tricky function. When you try to visualize it, it doesn't give you a good feel. But under the topic of distributions, it's a very well-defined object. It's just a matter of whenever you want to see the details of it, you have to make a big machinery, or you have to enact a big machinery into action. But let's see broadly, how do we see that first? So let's say delta function. This is delta function. It's delta. Often this is written as explicit delta. Whenever we don't have a font for delta, it is typically just capital D, delta function. It's often called Dirac delta function. That's also a good point to point out. So it's Dirac was the person who really started using it in the modern way we look at it. So Ken, have you seen delta function before? You might have used it here and there, right?
Yeah, for sure. I mean, especially, with simplifying other functions, you can use the delta function to do that simplification process where the x prime equals x, thus it's 1.
So that's whatever you said just now. That's pretty much the kind of use we want. But let's, while we are here, let's try to define it. So let's say we have a function. So let's call it, let's have a f of x. And this is a function. We define it, it's best defined graphically. No, let's say this is height h, right? So it is, let's say its height is 1 over h if x is less than h over 2 and it's greater than minus h over 2. And it is 0 otherwise. Feel for how far you can see. So that here and yeah, okay. So if I were to plot this function, that's my y-axis, or this is I'm plotting f of x here on the y-axis, and this is x, and somewhere here is h over 2. That's h over plus h over 2 and minus h over 2. That gives us the length of this base to be like h. And whenever x is within that, height is, let us say, the height of this function, and this is 1 over. And it is 0 otherwise. So everywhere else, it is 0 exactly. 0. It's not a continuous function, so the dotted lines that represent that. That's good. And now let's say, let's consider the limit h tends to 0 of f of x. So that seems to be very odd, because when h tends to 0, this whole almost the function is 0 everywhere, like except at h equal to 0 itself. And right at that point, this since the constant value also decreases, so that also goes to 0, or it reduces down to a point, but that point moves up, right? Because as h goes to 0, that goes to infinity. So it seems like, let me write it this way. So since infinity is not really comforting, not because it is anything bad, it's just that we don't know how to properly do algebra with infinity yet. Some of the infinities are good, some the different kinds of infinities. And what I mean by that different kinds of infinities is that how does it grow? Right? In the sense that as h tends to 0, this grows like 1 over h. I could have another infinity which grows like 1 over h squared, another one which grows like 1 over h cubed, and all those in some contexts might behave differently. And that's what I mean by there are different kinds of infinity. They might be different kinds of orders of largeness. So that grows to infinity for sure. And this says now, if x is not equal to 0, or if is x equal to 0, right? So as you reduce this h, the only point that remains is x equal to 0, and it's equal to 0 otherwise. Or now we can say it's x not equal to 0. So in that sense, if I were to draw a pictorial diagram for that, say that, oh, this is x and x goes to infinity. Here I write at one point. That's also fine, except for this discomforting feature. But this has a very, very interesting feature in there. Now, if I were to take the area, right? So let us say we talk about the area under this graph. So this is area under this graph. That's equal to, that's just a rectangle. So it is width over height. So the width is h, and so that's h, and that's 1 over h is the height. That's equal to 1. And the way it has been chosen, it's remarkable that it is actually independent of the height h, which means to say that if I were to, so this here also there is a rectangle, right? As h tends to 0, this rectangle is really infinitely long. So there is a rectangle we are talking about, whose height is pretty much 1 over h, and this is h, which is longer and longer. This is 0 times infinity, that's equal to 1, right? So that's the special feature about this delta function, that it is not any arbitrary infinity. This always try to cancel that h in it. So let's make this more definite. So if that is, and this is not a unique construction, we can have many constructions for delta function. And I'll give one more example. We can have lots of examples like that. Let's say, so now we will say, so delta function, the way it is defined, so this will be equal to exactly like this. It doesn't really have to be using this function. At x tends to 0 in some limiting form, this is equal to infinity at x equal to 0, and it is 0 otherwise, right? X not equal to 0. And one more feature, that if you integrate this function, which is what you were mentioning, you can do something with this delta function to define, you said a rescale function, right? Something like that. So that's let's say all the way going to minus infinity to plus infinity, doesn't matter. That's equal to, notice what is happening, dx here, when we integrate, we split this x variable into small pieces, and we take the limit n tends to infinity, and this differential element really goes to 0. That is the understanding of an integral. If you're doing numerics, you always see that you will break an integral into many pieces and you add up contribution from each piece. That's the tiny element, and in strictly speaking, you have to take the limit n tends to infinity. And what you're saying here is that delta function cancels that exactly. Whatever this is, that small element, this is 1 over that, and it exactly cancels out. That's a very fine cancellation there, that just gets independent of h, and that's your delta function. That's 1. It doesn't really have to be minus infinity to plus infinity. In principle, there are other ways of defining it. For example, you could say a to b dx delta x is equal to 1. So instead of, like, the way I have done it here is that I have defined delta function in 3 steps, right? First, it should go to infinity at x equal to 0. It should go to 0 at when it is not equal to 0, and the sum should be equal to 1. Instead, you can say this is equal to 1 if a is how do you say, if a is less than 0 and b is greater than 0. If you get such combinations, that's equal to 1. Otherwise, there are other combinations that's equal to 0. That means to say if both a and b are on the left-hand side of x equal to 0, then it doesn't contribute. If it's on both, on the right-hand side, that doesn't contribute. And then, and that way of defining, you don't have to really put this in there. So that's a basic understanding of delta function. But as you pointed out, we don't need these details. We mostly need this integral form there. But before I reach there, let me actually give you one more example. This is, one might argue that, oh, that's not really a good function. I have a discontinuity in there. Can we do this better? So a more a continuous function that can do the same job is, let's do another example. Let's say f of x, no, this time is equal to, let's say, let's say is, I think, so this is x square plus epsilon square. X was equal to 0, so I want, so this is epsilon, okay, on top. Where epsilon is a constant and x square, 1 over x square has this, this is a Lorentzian function, if you want. So if you were to plot this for a constant epsilon, this will look like this. So this is x, and that's f of x. And the epsilon has a nice interpretation here. This is kind of the width of this Lorentzian, has a measure of epsilon in there, and it's clear that as epsilon tends to 0, if that is the case, then this, and actually height also depends. It's not strictly like the earlier example, but as you take epsilon tends to 0, the height actually grows. How do you see that? Let's take a limit, right? So let's see, limit epsilon tends to 0, f of x. Again, this example is pretty much exactly the same as the other one. It's just a more continuous version of that. Earlier there's a discontinuity, and someone who's very skeptic, I think, oh, this is all because you're working with discontinuous functions, otherwise this will not happen. So when epsilon tends to 0, let's say, first let's say set x is equal to 0, let's say. x is exactly equal to 0 to begin with. If x is equal to 0, so that's 0. So you're taking the limit epsilon tends to 0 of epsilon over 0 plus epsilon square. So it's you set 0 to begin with. So that's 1 over epsilon, so that's infinity. So you again capture the fact that that's infinity. But now let's do the case x is not equal to 0. If x is not equal to 0, again you take the limit. Epsilon tends to 0 of epsilon over, now this is not 0, it could be negative or positive, but if it is not 0, you can always neglect epsilon square, right? If this is not 0, in the limit epsilon tends to 0, this will eventually get smaller than x. It will get significantly smaller than x. You can neglect that, and that would make this 0. Because then there is an epsilon in the numerator, and that actually makes it 0. And that has now the feature of our delta function, right? But then we said we need to verify one more thing, and that is that its integral has to be equal to 1. And that reminds me, actually, I think I need a constant also here. So let me put a 1 over pi in front of it. It's not relevant in the analysis that I did till now. So let's say 1 over pi, so 1 over pi. First everything goes through. But the next step that I'm going to do that with part of it. So let's do integral. Let's go minus infinity to plus infinity dx limit epsilon tends to 0 of f of x. If everything is convergent, and we're going to show that this is equal to 1, even though one piece here goes all the way to infinity, but as you take the limit, it goes to infinity at the very end, right? So this is this very fine change. One should be careful about this. One should criticize. But if I assume that I can actually change the order of limit and dx, most often it can be done, but sometimes when there are divergent quantities, then one has to be more careful. So with that caution there, if I proceed and do that, change that order, and f of x here is epsilon 1 over pi also, epsilon over x square plus epsilon square, and there is a 1 over pi. So that's the integral you get, but that integral can be done using elementary substitution. Substitute x is equal to, let's say, tangent theta, or actually epsilon tangent theta. Then dx is equal to epsilon secant square theta, and there is a d theta also. And we also need to worry about the limits when x tends to infinity, and x tends to, let's say, plus or minus infinity. Then angle theta is, so if x is infinity, what value of theta will give you that infinity? That's pi by 2, right? So it is plus or minus pi by 2. You want plus or minus infinity. With those, with that information, if you want, you can do this integral. So let's limit epsilon tends to 0. When x goes to minus infinity, angle theta goes from minus pi by 2. X goes to plus infinity, theta goes to plus pi by 2. Dx is epsilon secant square theta, d theta. And there is one more epsilon in the numerator, which I say this is epsilon square. Divided by x square is epsilon square tangent square theta plus epsilon square, and that is an overall 1 over pi. Interesting part is that there is an epsilon square in the numerator, there is an epsilon square in the denominator, that cancels out. Exactly like what happened earlier the height h of that rectangle canceled out. The height and the width exactly canceled out. Here also epsilon cancels out from numerator and denominator. And then the limit epsilon is not relevant, right? You can remove that. In fact, the denominator and numerator even cancels out in the theta dependence. Secant square in the numerator and 1 plus tangent square theta is also secant square. That's the same in the denominator. So overall, this is equal to, yeah, I can write one more step there. So overall, this is equal to 1 over pi, that pi I bring out all the way out, and that's minus pi over 2 plus pi over 2 d theta. That's exactly equal to 1, which is exactly what we wanted to show that this is a delta function. So that's an example of a delta function. Any questions or comments at this stage?
I don't believe so. Thank you.
But as you said, Ken, that this is all formal description of delta function, very good and very necessary for understanding it. But as when it comes to usage, it is done at a much more simplistic level. It's almost as a prescription. So what we have is, so one of the defining characteristics of delta function is the x delta of x is equal to 1. Extend this, it doesn't have to be positioned at x equal to 0. You can move it around, right? Just substitute x equal to x minus x prime if you want. So you can also say that this is equal to dx times x minus x prime. That's also equal to 1. It doesn't matter, it doesn't change anything. This is if you want translational symmetry, right? You can substitute x equal to x prime minus a new constant, and that will change that description, and that's equal to 1. If we use that, we can now multiply this with a function as far as the function itself doesn't go to infinity at x equal to 0. So then you will be evaluating it that point, and that will be infinity. So this is equal to f of 0. Why? Because again, look at this delta function, right? Delta function is 0 everywhere else. So the only place where it can contribute is x equal to 0. So that's infinity, but that infinity cancels out that dx, right? So that's balances it pretty much. So the value of the function there is captured. Same thing you do it here, more tiny generalization. That's the x delta of x minus x prime. And if you have an f of x, so this is equal to f of x prime. And that's all we need. You can actually ask from this point on, proceed further and ask what is minus infinity to plus infinity, dx, f of x. So now we can ask a lot of questions at this stage, or generalize this in many ways. One could ask what is ax plus b? What if there is a constant a? And this part I won't go through in detail. Let me put this as a quiz. Try to go through this feature somewhere in a textbook or somewhere, and try to derive this part, that this is actually equal to 1 over a times f of minus b over a. Because delta function is defined for minus, right? X minus x prime. So it is. So basically, you get the root of this equation. When does this argument of the delta function go to 0? That's the main factor. But then you pull out an a here, and not only that, there is one more feature. This has to be a magnitude of a. Try to understand the fact and try to derive the feature that y is magnitude. So that's your quiz, let's say. And there's one more thing I wanted to say. And a few more. So we did, let's say I is if you have an integral of, let's say, minus infinity to plus infinity. Let me say a to b, x, x, f of x, delta of x minus x prime. So this will be a function of x prime, will be equal to f of x prime, provided x prime is less than a. A little more precise version of whatever we did earlier. 0 otherwise. Okay, then we can ask, what about this? B x of x, and I have a derivative of a delta function. Okay, then you can ask, what is that going to be equal to? And it's very tricky when you want to imagine a derivative of a delta function, but very intuitively, very naively, one has to be very careful when you implement this in serious work, especially when you're in a territory where you're treading for the first time. Then you want to be very careful with the results that you get, because you could get wrong results. But the point is, now let's say you can define a function of this kind. So this is called a step function, right? Are you familiar with a step function, right? It is 0 everywhere, and this is equal to 1. So this is x equal to 0. This could be your x-axis, right? And that's your y-axis. That clear? So it's 0 if it is less than 0 and 1 otherwise. So that's called a step function. So this is step function. So you say this is 1 if x is greater than 0, it's 0 if x is less than 0. And right at x equal to 0, you keep it open. And then you can ask, oh, what is the derivative of the step function? And what would be the derivative of the step function? Notice that it is flat everywhere, which means that the slope is usually the derivative, right? Derivative is slope. Slope is 0 everywhere, right? Except at x equal to 0. And at x equal to 0, it's not very well defined, but then we could imagine this step function to be built out of a curve here, right? And that limit is taken in the extreme limit, that becomes a step function. And think of a smooth function and some limiting factor, and that way you can say that the slope becomes infinity at that point. And in that sense, you can define delta function to be at some abstract level, at some intuitive level, you can say delta function is a derivative of a step function. If that is the case, so now delta function has this structure, right? And again, this goes up, right? So it is getting squeezed from both sides, and the height is going to infinity. So that's a intuitive representation of a delta function. And then you say, what is derivative of delta function? Now we're talking about derivative of a delta function. What is that equal to? Again, graphically speaking, think of the slope. So slope comes 0, 0, then it goes all the way to infinity, but then again it goes 0 right on the top here. It again goes to 0. So it does go up, but then it comes down to infinity. So it seems like delta function has this feature that it goes to infinity and then goes down, and then it comes down and does this feature. And again, it goes up, right? It goes to infinity up there, goes to negative infinity down there, because while it is coming down, slope is negative. And you can take this further, and you can take second derivative of delta function, dx squared, and you have more overlaps in here, right? So you would say this is this. In a sense, what you're saying is that each of these infinities has some feature in there. And this is useful in some constructions. This comes out very useful, especially when you're doing electromagnetism. This will be a representation for a charge. This will be a representation for a dipole. This will be a representation for a quadrupole, and so on. Right? But we don't want to get into those things at this point. I just wanted to give you a feel for what I mean by derivative of a delta function and how you could intuitively imagine that. Algebraically, it's much easier to handle. We want to evaluate this, correct? Again, in the very limiting case, now it seems like there are 2 points that that contribute. Very broadly speaking, area is the integration, right? So if you were to integrate this quantity, there's a positive quantity coming there, negative quantity coming there, and if the function f of x is an even function, and maybe it is 0, right? So all those features can be analyzed, but let's do this algebraically. Geometry is good. It gives an indication or a feel for what we are doing. Let's proceed and let's do this algebraically. How would you do this algebraically? I know how to work with delta function, right? At this point, we are accepting that we understand this. Right? From that step, how do we go ahead? I say I understand delta function, so, but I don't understand derivative of delta function, how to operate that. So what I do is I integrate it by parts and get this derivative on the left-hand side. So let's do integration by parts, and we shouldn't forget that integration by parts always comes with a surface term, right? There's a total derivative term that comes in. So the integration by parts gives me a to b, x, and one way to look at integration by parts is take a total derivative, right? So instead of operating on delta function, operate on both. That's obviously not correct. This is not equal to this because here derivative acts on the function f of x. Here it acts only on one, so I have to subtract it out. That's one way of looking at integration by parts. So that's a to b. I have to subtract out that quantity. So this is df over dx. We operate only on that, and then delta function. Okay. Hopefully that's not squeezed too much in there. That's readable. I think so. Okay. That's a new function in here. Right? This is a new function. I know how delta function works. As far as this function is not having some weird feature at x equal to x prime, if it is not infinity, basically, that's what we are saying. If that's not the case, if it's well defined, that's the word we use. If it is well defined at x equal to x prime, then we know how to do the second part of the integral. And let's go to the first part of the integral. We'll come back to that first part of the integral. So the second integral is simply derivative of the function evaluated at x equal to x prime. And the first part is a total derivative. So whenever you have a total derivative, it contributes only on the boundary. It is plus, so it contributes only on the boundary. So basically this dx, this goes away, and that's a total differential, and the integral can be done, and it contributes only on the boundary. So it's x minus x prime. And you want to evaluate this whole thing at x equal to b and at x equal to a. Our delta function, we said, is x is within a and b, right? That's how we defined it. So x prime, we are saying, is less than a and b. If it is less than a and b, this is 0. Right? At a and b, this is 0. So delta function is never going to contribute at a and b. That's assuming that this x prime. So let's say left, the left, right? So let me say, or this is equal to minus df by dx. I can also say x prime, right? If x prime is less than b and less than a, or else it is 0. Like this fact that x prime is less than a or b takes away the feature that this contributes. So the moment I say that is the case, then I'm good. And actually, it is 0 if it is right at x equal to b, so that could be contributions, right? So let me say, yeah, let me just say just this much. Let me not say anything else. That could be a non-trivial feature when x is exactly equal to b. So if the delta function is right on the boundary, then maybe there is a contribution that is coming from here. So just to avoid that feature, let me say we are working with the feature where x prime is less than a and b. Usually a and b is at the infinity, so that's one point. Often it is somewhat. Okay, is that clear? Any questions on this? Ken?
I think it's pretty clear. Thank you.
We can extend this very easily. And so each time you differentiate by parts, you get a negative sign. So in general, we could say, or we could generalize this very easily and say you have more derivatives, n over the x raised to n of delta of x minus x prime, a to b would be equal to minus 1 raised to n times dn over dx raised to n times f of x. Oh, I should say f of x prime, because it's evaluated at x prime. Okay, let's pretty much repeat this again and again. Okay, so that's all delta functions. So that should give you more confidence with whatever we are going to be doing next. Okay. Okay. Okay, let's do an example. The first example is, let's say, I is equal to, not I, because now we want to do functional. So this is a functional. No, so I or f, f, it is a functional of u. And by u, I mean the square brackets that represent that this is a function of a function, of all possible functions, distribution of functions, if you want. And this is a, x1 to 3. X times a of x times u of x. That's what we would like to differentiate with respect to a function. So let's say the way you would go about is you want to do functional derivative f u with respect to u itself, but a particular function. So that's a particular. So this is a small change in the function. So this is straight line. You have this going from A to B, and that's a function. That's also a function. That's also a function. This is all u of x, right? This is u of x. That's u of x. All possible u of x. And you make a small change in the function. And when I say small change, I could go from one function to the other function, and then the difference between the two is the small change. And often you will represent as, since it's a small change, you will say this is a small change, right? Disturb it at every point a little bit away. So let's say a plus, and to show that it could be plus or minus, you show it as going around that value. But it doesn't have to be always plus or minus anywhere. And even often you assume that this is fixed at the boundary, and which is what we will also do for a couple of weeks, not because we cannot handle that at this point now, just to avoid new concepts that are going to come in. So let's make it simple at this stage that at x1 and x2, the function is fixed, right? For u of x1, u of x2 is constant, and we don't change that for every possible function. Okay. So how do we define this? You would say this is limit delta u tends to 0. So the limit delta u tends to, there's an x dependence there, so x tends to 0 of, you make a small change. So when you make a small change, this becomes u plus delta u. And then you subtract it. What's the change in the functional due to a small change in the function itself? So this is the small change. And any arbitrary change in the function. It's not a one particular function in there. So what is that equal to? It's limit delta u of x tends to 0, 1 over delta u x. And integral of f of u plus delta u, this is x1, x2, x. I've already used x outside, so I should switch over to x prime. So this is x prime. And u plus delta x, so this is u of x plus delta u of x prime. That's a change in the function, and then I have to subtract it out. So it's x1, x2, dx prime, a of x prime, and u of x prime. That's your change in the functional. Notice the first piece here is exactly the same as the second piece there. So I subtract out by saying this cancels out this. Again, if you recall your derivative, the simple classical derivative of a single variable that also has this feature all the time. That's equal to limit delta u tends to 0. Like this is delta u x if you want. And that is 1 over delta u x. 1 to x2, x prime, a of x prime, and delta u x prime. That's it. But we can make this, we can evaluate this better now, and that's where the delta function comes in. Now you go take this inside in here. Because it's x dependent and the integral is x prime, so we can actually do this. x1 to x2 prime, A of x prime, and we say this is limit delta u of x going to 0. And then the question is, what is this feature? So notice, what are we talking about here? So that's, again, there is a function u of x. So that's your u of x. And somewhere we make a change. So this is a change. This could be one of the possible changes. And what is delta u and delta u x prime? So this is at x equal to x prime. So let me this is x, and there is an x prime somewhere close by. Doesn't have to be close by. This quantity here is the change in the function at x, and this point, this change here is the quantity delta u of x prime. A small variation here, small variation here. And we are saying that these two variations are independent of each other. They are not dependent on one another at all. They're completely independent variations we are making. And in that sense, that's 0. Since they're independent, this is equal to 0, exactly like you say partial derivative of x with respect to y is 0, right? We emphasized that last time. In that sense, that is equal to 0. And then so there's one caveat in here, right? Oh, if that is the case, then the variation between, so when you do this dy dx, x with respect to x itself is 1. That's correct, this should be 1. But then there are lots of variables in there, right? There is a variation here, there's a continuous set of variations. All of them has to add up to 1. All possible variations have to add up to 1. And to take care of that, you say that this is actually delta function. It is 0 when x is not equal to x prime, but it's actually infinity when x is equal to x prime. Why? Because you want to capture the fact that when you integrate out, that has to be equal to 1. That's at least at one place it is actually non-zero, and overall the area has to be equal to 1. So if you get that, capture that in, you say this is equal to delta function. And that's the key piece in this main derivation, right? This is a basic setup. And you say that's equal to a of x. Any questions here at this stage?
So the limit, when you take the limit of that delta function right there, yes, and then you make it. I mean, that's a standard thing, right? Like that's what you're looking for when like from the beginning to the end. That's what you're trying to do.
Exactly. Right from the beginning, that's exactly what we are doing, and I'm formalizing by saying that this actually is equal to delta function. That's the only small key there. With that formal connection, I will be able to go in every other next step, right? I will be able to use algebra instead of again and again coming and analyzing this. So that's why I'm trying to stress this feature, so that it is tricky in here because these are two independent delta of x. Again, x and x prime, if you were to have it discrete, then they all have to add up to 3, right? If there are 3 variables, 1 plus 1 plus 1 should add up to 3. And if I were to vary this at least with one of them, it should always give me at least 1. And that's exactly my point, that if x is equal to x prime, it should be 1 in principle. But then since I'm integrating, right, I'm splitting this continuous variable into lots of infinitely tiny elements. When that tiny element contributes, I have to capture 1 of them. For that purpose, I need a reason. And that is the reason for that.
I see.
Not a divergence in that sense.
And then that actually goes to infinity is the case, right?
it is infinity, but why is that infinity showing up? That's because we are breaking this continuous variable into infinite elements, right? And I'm saying that the integral of that has to be equal to 1. So this has to be infinity, right? Why is that infinity in the delta function coming up? Because the x times the delta function, I would like it to be 1. Only way I can get this to be 1 is that I've broken this into a small element. If I want a 1, I have to make that infinity. Is that clear?
Yes,
So
yeah, I see.
if x is equal to x prime, I have to get that 1. Right? So there is one piece which is not in, which is a dependent quantity. They are independent, but x is dependent on x itself, right? Is
Yes.
that clear?
Yes.
Right?
Yeah.
Think about it, and to capture that, you bring in a delta quantity. And that suddenly throws off, oh, what's an infinity, and you don't like that. But there's a necessity for that because it's a continuous variable. There are infinite variables. Okay?
Okay, thank you.
At a formal level, it's easier to accept. Once you accept that, then we can do a lot of things from that step onward. Okay? But one should try to get that clear. So, do ask me again if there is a confusion. But if you proceed further, let's do another example then, right? So we can do various examples. Let's say, what if I have f of u? And now let's actually uh, change this a little bit. Or before I do that, let me quickly do this, right? So what if I have a function f of x now? Think of x as like we have x as position, right? Position of time. We want to do mechanics here, right? So x is a function of time. And then the same problem that we did earlier would be instead of x, now this becomes t1 to t2 t, and a of t times not acceleration. This is not acceleration, this is some constant a, and times velocity, which is let's say this position at this point, xt. Let's not say a, not confuse. That's some c, right? Some x of t. What will that be equal to? What's a functional derivative of this with respect to x at t? What is that equal to?
Um, that would be equal to the limit, right, of x delta x of t
Yes.
to 0.
All that we have to do, but the answer immediately based on what we did last time.
Oh, I see. So it'll just be c of t, right?
50, right? And how do I get that? So we want to start getting faster at this. And the fact that there is an integral, this is a linear term, linear in x. Coefficient of the linear term evaluated at the value of time, whenever this is, that's what captures the functional derivative. That's a linear term, coefficient of the linear term, kill the integral, whatever survives. Kill the integral, kill the linear term, C of t. Right? So that's how you do functional derivative if you want. As we proceed, we will do it like that, right? And in that sense, we want to actually now do f of x, and our integral, let's say, is t1 to t2 dt, and let's say half x of t y. That's an x of t square. You would say, oh, if I were to do standard derivative with respect to x, I should get 2 times x, correct? And maybe the answer is 2 times, so there's a half already there. So is this equal to x of t? Okay. Is that clear why I'm saying it should be x of t?
Yes, yeah.
Well, let's see how it works. Whenever there's a confusion, we just go through it in detail, right? And after a while, we get more confident and we start doing this more casually. Right? So again, functional derivative, not writing the limit there. This is equal to delta of x of t. This is equal to limit delta x tends to 0 of f of x plus delta x minus of f of x divided by delta x at the value t. That's equal to limit delta x tends to 0 of 1 over delta x evaluated at t. And then we have the function going from t1 to t2, half of. Evaluate this, I'm doing t plus delta t, so this is, x plus delta x. So this is x as a function of t plus delta x as a function of t. Oh, I should not forget that this is t is an independent variable, so this all should be prime, right? Dummy. What? X of t delta of x t square and minus of t1, t2, t prime of x of t prime square. Hopefully this didn't go away out of the board. No. Okay, good. Like we do in the standard derivatives, that is, expand this out. The main trick in this whole thing, that expand this whole thing out. When I expand the square, the first term again cancels that. And whatever remaining is, there is a 2 terms with delta x in there. Right? 1, 2, dt prime. There's 2 terms which are identical because they are not operators. Like if you're doing quantum mechanics, then you would say, oh, this is an operator, that's an operator, and that has to commute and all that. So half cancels out. So there's a half and a 2 times x of t prime and delta x of t prime. And there is another term which I will just say is delta x squared. I don't care what that actually looks like, because whatever it is in the limit delta x tends to 0, since in the very front there is a delta x, that's going to be 0. That's not going to survive in the very limiting case. But then I do the same thing again here. From this point on, it's the same as what we did in the earlier board. That's equal to E1, 2, t prime, 2 and 2 cancels out, x of t prime, and we have limit delta x tends to 0 of delta x of t prime over delta x of t. But that whole thing is actually 0. 0 most of the time, except when t is equal to t prime, which makes it a delta function. So this is t1, t2, t prime, x of t prime, and that's a delta function. Again, here we have also used the fact that at T1 and T2 there is no variation in error. That sometimes gives non-trivial features, which we will see later on. And this is just equal to x of t, exactly like what we predicted. So once you get very comfortable with this, there's nothing wrong in looking at the first expression there and immediately saying x of t, and we want to be able to do that, right? In your homework and other places, especially like in the first homework, like in this homework, you cannot do that because I'm explicitly asking you to do that. But starting homework 3, right? You don't have to go through these details for the functional derivative, right? You can immediately go through the steps as if you're doing normal derivative and get the answer. Especially if you can get here, that's sufficient direct integration. But even that, you can skip. You will see what kind of problems you can do that. Okay. Okay, so let me do a few more examples actually. So
Dr. Sujesh, I have a quick question. Could you say why you made that 0 again on that del x squared term?
yes. So this one, right? So now there is whatever this is, there will be a function delta of xt prime, let's say. There will be another function delta of xt prime, right? And there will be a delta of x, right? X of t. These are 3 variations, but there are 2 variations on top and 1 variation in the denominator. This will always be smaller, right? Delta x we are saying is again small, but whatever it is a variation eventually. That's a small variation. This is like one of them, like even if you say at t equal to t prime, these are the same. So that will be exactly the same as this. But then this will always survive and set it to 0. It's the same as, let's say, I think sine of x, correct? Sine of x is equal to x minus x cube over 3, right? 3 factorial. This doesn't contribute in the derivative.
I see. Yes, thank you. Thank you so much.
I hope I answered your question. Maybe I can remind you. Like, let's quickly do a sine of x, correct? Derivative of sine of x, the standard derivative, like classical calculus, right? How you would do this is take a limit delta tends to 0 of sine of x plus delta minus of sine of x divided by delta, right? And that's equal to limit delta tends to 0 of 1 over delta. And now we expand, right? Sine of x plus delta, what is the expansion? Help here. What is sine of x plus delta expansion? What I can do here is, how do we do this? We actually expand it out as, I shouldn't use trigonometry, right? Yeah, let's expand this. Yeah, so you would say series expansion of sine x plus delta. That's x plus delta minus x plus delta over 3 factorial, and then plus x plus delta pi over 5 factorial, and so on. And there is exactly similar piece coming on the other side. That I think that's going out of the board. That's equal to x minus x cube over 3 factorial plus x raised to 5 over 5 factorial and minus and so on. Okay. Good. And now let's try to collect all these things. At least try as much as we can do. I have to do this carefully, but 1 over delta. x cancels x. There is a delta that survives in here. That's delta. Now, again, x cubed cancels. The first term cancels the other one. What's the next term that survives here? Let's do that carefully. That's 1 over 3 factorial. And this is 3x squared delta. Right? Notice the 3 coming out correctly in there. And the next one is going to be delta square. So I don't, whatever it is, there is a delta square in it. And that's order delta square. That's the language. You see what I'm saying? The next term is a delta square. I don't care what that is, but that is delta square. If you can accept that. There are two more terms, right? First term I cancelled. The cube has 4 terms. First is a delta, then there's a delta square, then there's a delta cube. Do you agree?
Yes.
And similarly, the next term will be, this is minus, so this is plus, right? Plus 1 over 5 factorial times, this will be 5 x raised to 4 delta. And again, there are delta square terms. Like delta square means that all the other terms are at least delta square. Are you good?
Yes.
Now I see that, oh, okay, what is this all equal to? Limit delta tends to 0, 1 over delta. There is a lot of delta terms. So this is, I pull this all together. That's 1 minus, that is a 3 cancelling out very nicely. So it's x squared over 2 factorial. The next one is x raised to 4 over 4 factorial, and so on. And whatever I've left out is at least delta square. So this is what you're asking, what is that delta square? Why am I not keeping that? Notice, now you take the limit. When you take the limit, this delta cancels out. So this survives. But the next one, whatever that is a delta square. One of the deltas cancel out, the other delta will take it to 0 in the limit.
I see. So you just don't care what is in front of that.
Exactly.
I see.
Unless it goes to infinity, if you are talking about a function that can go to infinity at delta tends to 0, then you have to worry about it.
Yes.
And it happens, sometimes it does happen, but derivative is always a leading order that matters. Leading means the first cancels out, the first 0th order cancels out, the leading means the first order in delta is the one that balances this 1 over delta. Otherwise, you would think that this is 1 over infinity, but these two kind of exactly cancel out. And rest everything is 0 in the limit delta tends to 0. And that's equal to cosine of x. But that this is going to 0, it's not an approximation. This is in the limit delta tends to 0, that's exact. Is that convincing?
Yes, thank you so much.
Okay. So let's do one more example. So f of, let's say, x of x actually is t1 to t2 t, and let us say, what did I think in your, let's just c of t and dx over dt. Same idea as earlier. If I'm taking the functional derivative, Since we have done this a few number of times, if I jump a few steps, this will lead to delta x tends to 0, 1 over delta x of t, and then the limit, or not the limit, the difference between the two. That's dt c of t so c of t times d by dt of x of t. Now that's the change I'm making, plus delta x of t. That's the change, and then I have to subtract out 1, t2, t. Oh, I have to make t prime. T prime of t prime c t prime dx t prime over dt prime. Again, these two cancel out. This term cancels exactly that term out, and whatever I have remaining is the limit delta x tends to 0 of 1 over delta xt, 1, 2, prime c of t prime, and this is derivative d by dt prime of delta x t prime. Everything is with respect to t prime, the differentiation and the integral. So take this whole limit inside t prime c of t prime by dt prime. Now limit delta x tends to 0 prime over delta xt. But that's delta function, correct? That's equal to. But it's not the way it came earlier. This is a derivative of a delta function. But we know how to operate that. Just integrate by parts and do the details, but that's just derivative of c as a function of time with a negative sign, because we can use the property of a delta derivative of a delta function. And that's it.
Dr. Shajesh, where did the negative come from?
Oh, because remember the beginning of the lecture, we defined how a delta function operates. Derivative of a delta function. Where did the negative sign? By integration by parts. So
Oh.
let's do this two steps. This is equal to d1, d2, prime, d by dt prime minus d1, d2, d prime. This is the actual differentiation, so this is prime. This is equal to, you're saying that if t prime, or if t is less than t1 and t2, so we are saying t is less than t1 and greater than, or greater than t1 and less than t2, then this is 0 minus, of this we know, t. Does that help?
Thank you.
Very good. And that's all, I guess. Yeah, let me stop here. Hopefully this helps with the examples, and I will be doing a lot of this. So slowly we will get hopefully comfortable with this and start doing more quickly. Okay, Ken, we good?
Yeah, yeah. I think I got this. I'm gonna probably get some more of that. I'm gonna attempt that homework again before like we meet at 3. So this kind of helped me out a lot with some of the problems I was having.
Okay, good, good, good. Yeah. But anyway, let's meet and let's maybe small things we can talk. Okay.
Cool. Yes, perfect. 3 p.m. today, right?
Postpone it also, no problem.
Okay. So is it okay if we meet in the room like last time?
Yeah. I mean, I
Okay.
was only discouraging it. So let's talk about that. So yeah, it's not that I'm against meeting at all. It's just I don't want to completely say that, okay, come to my office. Last semester I did that, and every other moment I was having students. And when it comes to the university policies, there is a slight issue with that if everyone shows up. So that's why I was kind of discouraging. But it seems like you're the only one who is really showing up in my office hours consistently. So I think it's okay. So just feel free to come anytime. It's just that in the mornings, I'm not coming to the office. If you can give me a warning that you'll be going to be coming, I'll come to the office.
Okay.
See what I'm saying? Or I was thinking of changing the whole thing, but I'll just be in my office all the time. That's the best. Okay.
Okay. Okay. Sounds good.
So don't feel hesitate to come to the class or come to the office. I'm discouraging, but at the same time, if it's few people who really want it, should come.
Okay. Yeah. I mean, just in person kind of helps me out a
Of
little bit
course,
more than yeah.
I understand. I understand. Even in the classroom, don't hesitate to come to the class if that is more beneficial.
Okay. Okay. Cool. Sweet.
Just that I want every student to cross that line that only if it is very beneficial you come, otherwise you stay at home. That's the way I'm trying to do this. So if you
I
feel it is
see.
more beneficial to come to the class, do come to the class. Okay,
Okay. Okay. Cool. Sweet. Thank you so much, Dr. Shujaj.
okay. Good. Ken. Okay, I'll close at this point. Okay.
Okay. All right. I'll see you later.
See you later. Mhm.